sequences. So first I will define what sequence is, and then we will study its properties, mainly convergence and all those stuffs. So first let's concentrate on what is a sequence. So take this set domain as natural number. That is 1, 2, 3 and all this, and take the codomain as assign every one real number to 1 real number to 2, and continue doing this. So in some formal mathematical sense it becomes that it's a function from natural number set. It's a function from natural number set to the real number. So this defines function. So the next thing comes, so to get some good knowledge of function, we always draw it. Okay. So next thing what we are going to do is to draw the sequence, how it looks on an XY plane graph. So first thing we learned is this is the definition of a sequence, rather real sequence. Because there exists it depends on the codomain. When the codomain is complex and others some set, so it depends on that. It's the most common real sequence. So now we will see how a sequence looks on a graph. How to draw it on a graph. So see that the natural number set is the subset of the real number set. So draw a function on of real numbers. I mean f from R to R. Draw it. So suppose I draw 1 by x. So it looks like this is 1 by x, f of x is 1 by x. Now what we do? Now to draw it neatly, so we cut it at certain intervals at this point, So all this. So we have that spot. So we are seeing a subset of it. So now continuing this, we will get like this. That's how a sequence will play. So it's 1, it's 2, it's 3 and 4 and so on. So we will write it here as f of n equal to 1 by n, where it's, so see there is a nice thing. The function 1, the sequence 1 by n actually behaves like the function 1 by x in some sense. When it behaves on the real, natural number. So it will be becoming more important in when we do further analysis, that if we know the behavior of the function 1 by x, because it's easier to get, we can do calculus over there. So if we can find the behavior of that function f x is 1 by x, so we can automatically transfer that some of the functional qualities or characteristics over to this sequence. So that will be discussed later. So the next thing comes. So what we study next? So next we study convergence. So what is convergence? What is convergence related to this sequence? So see, one of our major interest is how the function, or rather the sequence, behave when it grows large. When it goes to amount of t infinity. So that's our main interest here. So convergence is a study of the function at infinity when x goes larger, or rather n goes larger. So convergence type of, convergence is a very lower dimension characteristics. It contains less information. You will see that if we change one or two values of the sequence, the limit may, convergence may remain same. So it contains the lower information of the sequence. So now let's move on to the convergence part. So now we will study about convergence. what's it really is. Now, to study convergence in a nice, neatly way, we define two notations that not usually given in many books or rather lectures. That's we want to get familiar with the. It's a new understanding, new topic. So we want to get you all familiar with this neat, small, not very difficult, but concept that will be helpful to understand this convergence better. So that is simple. It's a definition of zero and infinity. So it may seem very obvious rather, but it's not. I mean, okay. So how to define zero? It's defined. Okay. So we can tell like this. Zero is the smallest positive number that is less than any positive number. Rather, zero is a positive number that is less than any positive number and greater than any negative number. So it's like x is defined to be zero if and only if modulus of x is less than a, where a is greater than 0. So I will write. Right. So it's very obvious, right? I mean, you take the modulus of the number. If it's less than any positive number, it's 0. So that's the main thing. I mean, it can be proved very easily. Suppose take that x is not equal to 0. So take x is not equal to 0, so x is equal to some else number epsilon. So now modulus of epsilon is never less than epsilon. So it's a contradiction. So similarly, it's you prove it by contradiction. So that's how we define 0. This concept is very important in the definition of convergence. Now similarly, infinity is defined as any number greater than any positive number. It's a number greater than any positive number. So that's it. So now it's a part. So now we come to the definition of convergence. So what is convergence? Convergence is the behavior of a sequence when it merges to infinity. So take a function f of n. Now we have defined the function. The next sequence. So now we will take the obvious usual f x equal to 1 by x. It will be helpful as I will tell you later lectures. Okay, so that's 1 by x1. So it's a function. So I take the natural number values. So it's a 1 and 2. Now, see, we may do it. So, as x gets larger and larger, this 1 by x gets smaller and smaller. So, actually, 1 by x, when x gets larger and larger, 1 by x gets smaller and smaller. So, and it's positive. So, it's that 1 by x is getting lesser, the modulus value of the 1 by x, that's the 1 by x is lesser than any positive number. So in some sense, when x gets larger as s tends to infinity, that modulus of that value less than any positive number. So it's equal to 0. So and we can also see with the graph. So now we will define it formally in some sense. So we don't know the limit. Okay. So let the limit be L. That is the behavior of the function at infinity. Right. Now, this is how it goes. Now, I want you to concentrate on this thing. That see, so you know, okay, let's assume that here the limit is 0. So here L is 0. Now see, one interesting thing is, you take any, any ruler or any bound over this interval. So like this, a strip of line along this. So it's L plus epsilon, it's L minus epsilon. Here it's okay. Now see that after some time all the numbers are getting in this line, all these numbers. So after this greater than equal to this number, suppose it's called n. So after this n number, or it's all those things are greater than are in this strip of line. And as you will see, as the length of this strip gets smaller and smaller, obviously number increases. So it's a new f minus epsilon 1 minus plus epsilon 1 and minus epsilon 1. So concentrate on these only. So see, for the new epsilon, this n is getting larger. Previous one it was here, and now it's getting larger, n dash. Okay. So we go like this. Take an epsilon. So take an epsilon. Pause this. You see the interval L minus epsilon to L plus epsilon, and for that interval you will get an n, and see as a epsilon changes, n of that n also changes, so it's a function of epsilon that becomes natural number. Now for that epsilon we got an n or epsilon here. Okay. So it's that for all n greater than equal to this, f of that natural number is lying in this bound. So it's coming formally, writing it mathematically is for all n greater than equal to this n of epsilon, modulus of the distance between that we are defining a of n minus L. So that's the sequence is a is less than epsilon. So I mean this is equivalent to this. It's lying within this strip of line. That strip. So let's rub this one off. So for now it happens for all positive numbers. So we put sign up for all natural numbers for all positive numbers. As capital and as epsilon changes, so n of epsilon changes, as we have shown in the diagram. I mean, if you take a smaller strip, the n of epsilon shifts here. That's it. So we will all continue in the next lectures how we will take examples and all that stuff. So let's give some examples. Okay. So we will just prove our intuition about the function, how it behaves with the natural numbers. We will now analyze the convergence of this function, which intuitively we prove that its limiting sense is 0. So not this function, that's a sequence. So I have drawn this function, let's say, to see it there. So what we have to find we have now there are some steps to solve it. Okay. So first we have to fix an epsilon greater than 0. So suppose epsilon equal to 0.1. Now for that epsilon, I mean here epsilon equal to 0.1. So we can assume, first of all, this is a bad point of this statement. Here we have to know from if we apply this to prove that a function sequence has a limit L. So from the early stage, you have to guess the limit. I mean, here we have to guess that the limit is 0. So we have to assume it, or we have to do it like that way. So that's a bad part of this. So we will talk in other lectures how this can be proved by Cauchy sequence method. So now we give an example of here. So we have to assume that the limit is 0. As your case. So now, for that limit we have fixed an epsilon. We have fixed an epsilon, and we have to show that for this epsilon we have to make a choice of n for this epsilon equal to 0.1 such that, and we have to make the choice of n. So how do I find it? So that's a definition. We have to satisfy that equation, that inequality rather. That's a n minus 0 is less than epsilon, so equal to 0.1. So now a n equal to 1 by n here, so modulus of 1 by n is less than epsilon equal to 0.1 here. So as n is positive, natural number is positive, so it's becoming n is greater than 1 by epsilon equal to 1 by 0.1 equal to 10. So for this, that epsilon, after n equal to 10, all those numbers after that will lie in the strip of length 0.1 on both sides of 0. So like this, all these numbers will lie, and that's mathematically proven. So now see, if you take an arbitrary epsilon, you take that epsilon, that natural number n of epsilon would be the next integer after this. So how would you define it? It's like this: the integer part of this plus the next integer. So n epsilon is defined as this. So it's done.